Before we could fit millions of circuits into our pockets, controlling the flow of electricity meant managing massive, room-filling machines. These early computers relied on vacuum tubes, bulky glass components that were hot, highly inefficient, and prone to constant failure. The modern alternative is much smaller and significantly more efficient: the microscopic, structurally perfect crystal lattice of pure silicon. Silicon is tetravalent, meaning each atom has 4 electrons in its outer shell. In a pure crystal, every silicon atom shares those 4 electrons perfectly with 4 neighbors to create tight, stable covalent bonds. This creates an incredibly rigid architecture. Because every single electron is locked into these bonds, there are 0 free electrons available to move through the crystal and carry an electrical current. Silicon's absolute structural perfection is precisely what makes it an electrical dead end at room temperature. Without a way to move charges, it acts as a total insulator. We can visualize this restriction using energy bands. The valence band at the bottom is where the bound electrons live, while the conduction band at the top is where they need to flow. Separating them is the forbidden band, an energy gap that electrons cannot occupy. Crossing this gap requires a specific amount of energy. In silicon, an electron needs about 1.1 electron volts of energy to jump from its bound state into the conduction band. In a natural environment, the only way to provide that energy is through heat. However, applying enough heat to force a massive electron jump across that 1.1 eV gap would literally melt the silicon crystal. This leaves engineers with a difficult question: how can we trigger electron flow without relying on destructive levels of thermal energy? To make silicon a useful conductor, we cannot rely on brute force heat. Instead, we have to intentionally break the crystal's structural symmetry from the inside. We solve the symmetry problem through a process called doping, the intentional addition of a tiny, precise amount of an impurity into the pure silicon. For this specific process, we use a pentavalent atom, like arsenic or phosphorus. These atoms are unique because they possess 5 valence electrons in their outer shell, rather than silicon's 4. As the doping process begins, this foreign atom locks into place within the silicon grid, occupying a slot meant for an atom with 4 electrons. The impurity successfully forms covalent bonds with 4 neighboring silicon atoms, allowing it to blend seamlessly into the existing architecture. But the 5th electron is now an orphan. Because it has no structural partner in the grid to bond with, it is pushed to the outer edges of the atom's influence, held only by a very weak attraction. By forcing a 5-sided peg into a 4-sided hole, we engineered a free agent electron that exists independently of the crystal's rigid covalent structure. Looking back at our energy map, we can see exactly where this orphaned electron sits. It occupies a new state called the donor energy level, located just below the conduction band. The energy required to free it drops from 1.1 to a microscopic 0.05 electron volts. At this scale, standard room temperature provides more than enough ambient energy to effortlessly bump these electrons across that tiny gap and into the conduction band. Because these pentavalent atoms freely give up their extra electrons to the conduction band, they are known as donor impurities. This microscopic trace of donor atoms bypasses silicon's massive energy barrier entirely, giving the material low heat conductivity that it could never achieve on its own. If we scale this up to the entire crystal, we find thousands of donor atoms releasing their extra electrons into the system simultaneously. This creates a massive, cascading flood of negatively charged free electrons swarming through the previously empty conduction band. Remember that in pure intrinsic silicon, the system was perfectly balanced. Every free electron was matched by a hole, or an empty bond left behind. However, this massive surplus of new electrons changes the environment. These free agents constantly collide with and fill in the few naturally occurring holes in the lattice. As these donor atoms release their electrons, their sheer volume actively suppresses the natural hole population, destroying the crystal's intrinsic equilibrium. This tips the scale toward a radical numerical imbalance, where the concentration of electrons is now vastly greater than the concentration of holes. In this new state, electrons become the majority carriers of the current, while the suppressed holes are reduced to minority carriers. Because the dominant charge carriers are negative, this engineered material is officially classified as an N-type semiconductor. This N-type silicon represents a fundamental building block of modern electronics. When combined with its opposite, P-type silicon, it enables the high-speed switching that defines the logic of every diode and transistor. By injecting a precise, calculated flaw into a mathematically perfect crystal, we achieved a level of control over electrical flow that makes modern digital logic possible.